right, so the topic is optimization. And in your handout, you should have basically the same information as to which steps we're going to be following when we're solving these questions. And like I said, this is a really interesting section. It's a little bit on the challenging side, but if you do lots of examples, I think it's a very fun section. You'll be amazed the level of problems you can solve here with a very basic information. And that very basic information is finding the maximums and minimums of a function. And how do we find them in calculus? How do we find maximums and minimums of a function? We just covered the graphing section, right? We did a lot of that, right? We set usually f prime equal to 0, right? Because that represents horizontal tangents on a graph, right? That represents points where maximums or minimums may be found. And we also, of course, sometimes do where f prime is undefined. But that's very simple equation. Solving f prime equal to 0 gives us some very important things about the function, and we're going to make use of that in this section. Okay, let's take a look at the steps of optimization. So basically, optimization is the process of finding maximums or minimums of a function depending on what is desired. For example, if you have a limited amount of material and you're going to create a can, let's say, from that material, maybe your question is, what should be the dimension so that I maximize the volume? You're trying to create as large of a can as possible from a limited resources. Or the question could be, let's say that you're talking about a profit function in business. How many items should I manufacture so I have the maximum profit available? And sometimes you're trying to minimize things. So say, again, it could be the materials. I want to create a box with a certain volume. How can I minimize the material use? How should I create my dimensions so I include that amount of volume in the container, but I use the least amount of material possible? So depending on the question, you're either maximizing or minimizing a given function, whether it's a profit function, the volume function, etc. And here are the steps that we're going to follow. First step is determine a function to be maximized or minimized. Read the question really carefully because they will tell me exactly what they want. If they want the maximum or the largest possible box, you're maximizing volume. If they want the least amount of material used, you're minimizing surface area. So read the question carefully. Usually they tell you exactly what they want. So write it down as a function. And then usually they give you enough information so that you can write that function in one variable only. So here you do a substitution. If there are two variables, get rid of one of them. And then the third step in every question is set the first derivative equal to 0. And here you're differentiating it with respect to x. Nothing is moving with time, like in the section related rates, you're differentiating with respect to time. Here you're just, it's like y equals f of x, like in the last section, like finding maximums and minimums of a function. You just differentiate the function with respect to x. You're trying to locate the lowest and the highest points of the graph, basically. So solve for x. And then once you have found that, it could be either a maximum, because solutions to that could be a max, or it could be a min, right? How do you know which one? Here is a suggestion that I have for us. There's more than one way. You could do the sign chart. If you're first increasing, then decreasing, it could be a maximum. But this is an easier way, I think. You don't have to do the entire sign chart. Whatever number you find in step 3, substitute into f double prime. If f double prime is positive, that means that the function is concave up. So the point you found would be what then? If the second derivative is positive, that means it's concave up, right? So the point found is going to be a minimum. On the other hand, if the second derivative is negative, then the function will be concave down and the point found will be a maximum. And usually step number 4 is the checking process. Usually by the time you get there, you already pretty much have a good idea about what the solution is. And also please read the note on the bottom of your sheet. Occasionally, the endpoints of the domain might also be used. Most of the time, the maximums and minimums are going to occur at the critical points. But there are very rare examples in the book. It might be like 1 or 2 examples in the entire exercise set where the actual maximum occurs at the end point. Now, have we seen an example like that in the last section under graphing? When we were finding absolute max and absolute min, right? what do? We check the function at the critical points, but we also check them at the endpoints of the domain, right? So sometimes that's also something good to do to make sure that you have really reached the absolute maximum. Or you can also look at a graph. If you do the graph and you can verify that the point that let's say you found a maximum and you were trying to find the absolute maximum. If you look at a graph, you will see that that is the absolute highest point on the graph. That can also verify that you have found indeed the absolute maximum, not just a relative maximum. Okay, we're going to do some examples. We're going to start with a very simple one that you don't even need calculus for. Most people guess this answer, but let's do it both ways. First by guessing and then by using calculus. That way, you will see that the methods we're using are really working, and then we can tackle more difficult examples. I want two numbers that add up to 20 and that multiply to as large of a number as possible. Okay. Before we do calculus on this, let's just do some trial and error. Okay. Give me two numbers that add up to 20. Any suggestions? We'll do a few trial error. 10 and 10 seems like the most easiest thing that comes to mind. 10 and 10. And what is the product there? 100. Right? Give me another possibility. 2 and 18. The product is 36, right? It's not as large as the previous one, right? We're trying to make the product as large as possible. 1 and 19. Still, the sum is 20, right? But the product is 19, not even close to the first one. So you could do all the, all sort of trial and error. It didn't even say it had to be whole numbers. You could try, 9.5 and 10.5 or things like that. But we have a pretty good idea. 10 and 10 is going to be hard to beat, right? It's a pretty large product. Now let's see what calculus tells us the answer will be. So you want two numbers. Let's call the numbers x and y. The sum should be 20. So x plus y must be equal to 20. The product should be as large as possible. So we want to maximize, and I suggest that you write this in every question. Write down specifically what is it you're trying to maximize or minimize. If nothing else, I will give you a little bit partial credit just for having gone that far in the problem. But most importantly, that will put you in the right direction to solve the problem. So always write down what is it you're maximizing. In this case, the product of the two. And the product of those two variables would be x times y. So if you like, call that the capital P function or capital F, the function that we're trying to maximize. The product function, I call it F in this case. So in almost every one of the questions that you study in this chapter, you're going to have two lines when you begin a problem. Okay, one line it says maximize this or minimize this. Okay, this is called your objective equation. This is what you're trying to maximize. Okay, then they give you extra information so you can solve the problem. The second one is usually called your constraint equation. They're giving you a condition that needs to be satisfied. Okay, so every one of these questions, whatever your objective function is, that's the one you're going to set the derivative equal to 0. Why? Because that's the one you're trying to find the maximums and minimums, right? So you need to know where those maximums and minimums exist. But before we can go to that, our step number 2 said, write the equation in one variable only. So let's do that. Let's write our objective function in one variable only. So f equals x times y. And instead of y, what can I write based on this equation? Y is 20 minus x. So basically, you come back over here, you solve for y up here, and then you substitute that back into this equation. And let's simplify it. The function we're trying to maximize is 20x minus x squared. Now tell me roughly what's the shape of the graph of that function? It's a parabola that opens down because of the negative x squared, right? So there's going to be a vertex. The vertex will be the maximum. But in this class, we don't have to memorize the formula for the vertex because we can do it with calculus, right? We can take the first derivative set equal to 0. That will give us the vertex. That will give us the maximum point on that parabola. So whatever it is you're trying to maximize, remember, that's the function you're going to be differentiating and setting equal to 0. In this case, this is it. Let's go ahead and do the step number 3. Set the derivative equal to 0. So in this case, derivative is 20 minus 2x. set it equal to 0, and solve for x. So we get x is equal to 10. No surprises there, right? We expected to get 10 and 10. But for these questions, it's very important. Always go back and read the question. Make sure you're answering what you're asking for. In this case, they said, find the two numbers. So don't just leave with x equals 10. Go back and also find y. In this case, y is 20 minus x. It's also 10. And sometimes they will also ask you, they'll say, what is the largest possible value for the function? Like, what is the largest possible product? What is the largest possible box you can create, the largest volume in that case? In this case, they didn't ask it, but let's also say that the largest possible product would be 10 times 10 or 100. But remember the checking step, which is step number 4. How can be assured that the point we found is indeed a maximum and not a minimum? Because both a maximum and a minimum have its derivative, has its derivative 0 at a local max or min, right? So let's do step number 4, the checking step. Take the second derivative of the function, and what do we get? Negative 2, right? Which is a number less than 0 everywhere, no matter what x says, right? So what does that tell you about concavity? That it's going to be concave down, and that the point we found is going to be indeed a maximum. And since it's concave down everywhere, there's only one local max. It's also the absolute max. So we can't do any better than that. 10 and 10 are the best two numbers to select that will maximize the product as 100. Okay, so again, that question, we didn't really need calculus. We could have guessed the problem. Let's do another one of what I consider a basic solution, a basic problem, and then we'll move our way, to the more challenging ones. This one actually is not in your notes. I'm going to just write it right now. It's a very similar one to the one we just did. The question is, the sum of two positive numbers is 9. The sum of two positive numbers is 9. Find the numbers if the product of the square of the first and the second is a maximum, is as large as possible. So the sum of two numbers is 9. Find the numbers if the product of the square of the first and the second is as large as possible. Once again, we're dealing with two numbers, right? So let's call them x and y. Let the numbers be x and y. What do I know right away? They add up to 9. So that's my first equation. X plus y is equal to 9. Okay. And then they tell us that the product of the square of the first and the second should be as large as possible. So, as large as possible meaning maximize, right? Maximize. What are we going to maximize here? The square of the first, which is x squared, if you say the first number is x, and the second, but they didn't say the square of the second, so it's just the square of the first number and multiply with the second number, so times y. So we're trying to maximize. Remember, every one of the optimization questions that you solve, you should have an objective function, and next to it you should write down maximize or minimize. Many times what I find is like students have difficulty because they have two equations and they forget which one was I was supposed to maximize, which one I was minimizing, and then they go back to the wrong equation, and then everything goes down the hill from there. So write down which ones you're maximizing. This is your objective function. This is the one you want to get in one variable only. Okay, x squared times y. Now you have two choices here, right? You can either solve for y on the top, or you can solve for x. But one is going to be easier. Any guesses which one is going to be easier? You think of the next step when you substitute it back in. Is it easier to substitute something for x or something for y? Easier to substitute something for y, because otherwise you have to binomial square the quantity. You know, that's going to be messy. So let's solve for y then in this equation. Y equals 9 minus x. So we're trying to maximize. Once again, let's call that function f. You could call it anything you like. So the function we're maximizing, our objective function, is x squared times y. And instead of y, what am I going to write? 9 minus x. Okay, what should I do at this point? Distribute it. So we have 9x squared minus x cubed. This one does not have such an easy graph to guess, right, because it's a cubic. Okay, what do we do now? Take the derivative and set it equal to 0. So the derivative is (18x minus 3x squared), right? Differentiate with respect to x. And what am I going to do with the derivative? Set it equal to 0, because we're looking for points where slope is 0, where the maximums might be occurring. Again, normally critical points can also come from points where the function is, the first derivative is undefined. But for polynomials, they're always defined, so there's nothing to worry about that. Okay, let's try to solve this for x then. Take out a 3x. So we have a 6 from the first one, and minus x from the second one. Okay, so we now set each one equal to 0. What do you get from the first one? You get x is equal to 0. And what do you get from the second one? X is equal to 6. Okay, if x is 0, what is y? Because earlier we said y is equal to 9 minus x. If x is 0, y is 9. And if x is 6, what is y? 3, right? Now, so it's either this pair or this pair. One could be max and one could be minimum. So our checking process will be helpful here. So let's go to step number 4, where you check for the second derivative of the function. Check the second derivative. What is the second derivative of this function? Take it from here, differentiate it one more time. Derivative of 18x is 18. Derivative of negative 3x squared is negative 6x. Now, this is not going to be positive everywhere or negative everywhere, because there's an x in it. So what we should do is, the two values that we got up here, we got this one and we got this one. One at a time, let's plug it in. Okay, so first evaluate this at the point x equals to 0. And what do we get? We get 18, which is greater than 0, right? Positive. So that means that the function's concave up. At that point, you're going to have a minimum. Then take the same second derivative function. This time substitute which number? 6. That'll be 18 minus 6 times 6. So that will be definitely a negative number. What is it, negative 18? So again, you don't even care what number it is as long as it's positive or negative. Negative means concavity will be downwards, and the point obtained will actually be a maximum. Okay? So we want to keep the 6, which comes, of course, with the pair of 3 as the second number. So we're saying that if the first number is 6 and the second number is 3, you will have the largest possible function f. And what would be the largest possible value of f in this case? If x is 6 and y is 3, remember the function was you multiply the square of the first times the second, right? And the first number is what we called x. So you're going to multiply the square of that times the second. And I believe that turns out to be 108. So this is the highest value for the function. So if you try any other combination of two numbers that add up to 9, x and y that add up to 9, we expect that we're going to get something less than 108 when you put it into x squared times y function. So the question was, what are the two numbers? And our answer is, the two numbers are, the first number is 6, and the second number is 3. Those are the two numbers that the question was asking for.